So that went quite well, didn't it?
Yeah, it did, I think so.
So we looked down at the lab, it smelled funny, and we did some chemistry things at Benzene, and we made Sprite.
Yeah, we're aiming for Diet Coke. I don't actually, do you like Sprite?
No, I don't like Sprite, I think anyone likes Sprite.
We're just going to tip that away.
We are, so we aimed Diet Coke, we missed.
Tesco has some though.
Tesco, you're probably just gonna, that's probably easier, right?
Yeah.
We also made some very nice acid crystals, they were cool.
Oh, I'm going to put them on my Christmas tree, they
yeah,
look great.
they look great. They might, like, kill your cat though.
Oh, it's okay, I don't have a cat.
Oh, that's okay then. So, with the things we did at Benzene, we thought, we're doing a few mechanisms, we're writing them down as we did it, we went, they need to know that for AG chemistry.
Yeah, so now we're going to teach you some mechanisms.
Yeah, we took the liberty of writing a few questions up.
We've got two different examples. We've got nitration and halogenation.
So we're going to go through these, and these are mechanisms you need to know. So right at the beginning, like AS, you need to know the conditions. You have a catalyst, H2SO4, and 50 degrees, you could write it in Kelvin if you really wanted to.
Yep.
But
it doesn't stop there.
It doesn't stop there, because in AS chemistry you knew that a catalyst adds an alternate pathway. But that alternate pathway is the one that actually starts reactions. This is what we have to start with.
Yep, and now you have to know this reaction with the catalyst.
You do. So the HNO3 doesn't straight react to the benzene, it actually reacts first with our H2SO4 catalyst. This forms two quite distinct charges which become quite important later on. So when they react, it forms NO2+, positive charge there, and an HSO4-. It'll also form a water, which stays at the end, so we can forget about that for now, because it is maintained.
So what's happened is a H and one of the O's from this this compound here.
Yep, and one of the H's from the sulfuric acid have formed water, and we've got two ionic compounds here.
So now this can react with the benzene, because this can't in this format, that just wouldn't do anything. Yeah. That's why you need this catalyst.
So it does, and like in all our substitutions in AS, it's because of the positive charge here and the mostly negative charge of our carbon structure. So we draw benzene.
Yep, way back.
Many centuries ago.
Have this benzene.
Yep, and it's just sort of chilling at the moment, and it's got an H as it always does.
Yep.
But our NO2 is attracted to this, but it's positive, so it needs...
I'll draw the H on. There is actually H's on all of these, but they're irrelevant for the mechanism.
Yeah, because it's C6H6. And then attaches, because it wants to bond here, because it's a vaguely negative charge in the ring.
So you've got a curly arrow going up.
Yeah. But because the negative charge is just dispelled on the hydrogen, it actually makes a positive charge in the ring, which you draw as a sort of horseshoe.
But make sure the tip of your horseshoe is at the carbon where this thing is occurring.
Yeah.
So if you were to draw it, say, that way, have the positive to this, you wouldn't get the marks if it's happening here, or if you're drawing it happening here.
And we call this step that's currently here the intermediate step, and it's very unstable because there's a positive charge and hydrogen is positive. It just wants to get out of there. So what happens next happens very rapidly. The hydrogen just runs away.
It does, and one of these two has to run away.
Yeah,
and the hydrogen runs away because this one is too strong of a bond.
Yeah.
Out of the two, hydrogen has to go.
So it does, so it leaves us just with our product here, and a hydrogen just sort of jamming about, which is an ion at this stage. But there's also our catalyst still as an ion floating about in our reaction. So these two sort of sort each other out.
So
and
there should be an arrow there, because it takes the charge there.
And the HSO4 bonds with the H+, reforming our catalyst, which is why it's a catalyst. And that's our reaction.
And you need to know all of that reaction, including this arrow going from the ring, make sure it goes and it's touching the ring, to the positive ion. Because it's going to give it an electron, essentially, make it back to a normal molecule rather than
that's why it becomes positive then.
And the hydrogen is going to take it. You can sort of think of it literally taking the plus. That's what you can think of it as. Then that reaction at the end is important as well for your full marks. There you go.
And that's one mechanism, but like AS biology, chemistry, all these are sort of reiterating, but with benzene we have the halogenation.
Yep, so I think I'll talk through this one, you've done plenty.
I think that's a good plan. Take it away.
Alright, so up here we have two catalysts. Now they don't both happen, it's one or the other. Just mentioning, you can either have this iron trichloride or aluminium trichloride. Which one have you? He's chosen iron trichloride in this case. Aluminium would work in exactly the same way, but where it says Fe, it's going to be Al. So, first you've got a Cl2 here. It can't react, just like here in molecule form, it can't. It has to be an ion for electrophilic substitution. So what it's going to do is going to give one of its chlorines to this. It's going to go up to Cl4. That's going to be a negative charge, because chlorine is negatively charged, has a negative charge to make, and Cl+.
Ta-da! Then we have our benzene just sort of chilling.
Yep. In fact, you'll find how similar this mechanism is to this one. Right at the start, you're just going to have a benzene with a positive ion near it. It's going to give it its electron. It's going to have an arrow going to the Cl+. There should be a plus there.
It should be, sorry.
So it's going to give that. Then you're going to have your horseshoe again. Again, make sure the top of the horseshoe is at the right carbon, otherwise you won't get full mark, or you may not get full marks. Especially if you've got a grumpy examiner.
And they're all grumpy examiners.
Yeah, because they want to be watching football or something, and instead they have to mark everyone's paper. So just be careful of that. Again, this is called the intermediate step. You might get a mark for that. If not, it's worth appreciating that's what it's called, in case it's a different type of question that doesn't require you to draw it, requires you to talk about it. Again, this step is rapid, it's very quick, and it's called the rapid across there. Out of the H and the Cl, the H can leave, the Cl is too strong of a bond, so the H has to go again to create a H+. And again, if you think of this as being in a beaker, there'll actually be hundreds and thousands of each of these molecules, but if you think of it as just one, the only thing left for the H+ to react that's unstable is this FeCl4-, which is going, so you're going to lose a Cl off there. Losing an ion would be ridiculous, because that's a +3 charge, because it's stable in a +3 state. So you're going to have to lose one of the chlorines. It's going to create hydrochloric acid and your original catalyst.
And that's the other mechanism, which is pretty cool. But sadly, they keep going on with benzene for ages.
They do. One final thing, make sure you put an arrow from the H to the plus, pointing that way.
You do. Sorry about that. So after this reaction, it goes on to further reactions and then stuff about phenol, which is pretty exciting new stuff.
Yeah, I like phenol.
I like phenol. I have to think on my toast, but apparently that's not good for you. Apparently not.